Yeah, I'm trying to get to it. I'll definitely have them up by the weekend. Trying to get that done today. So I'm hoping to have a reading list and another practice exam up today.
Good, because I am really serious. Don't sweat.
Oh wait, there's a lab today too, right?
Yep.
Shoot.
What?
Yeah, I don't have the lab up yet. It'll be at least a 2-week lab, so. Alright, I guess it's after 8, so for the activity, as more people hopefully are coming in, it's just write a program in C or assembly that outputs hello world to a computer connected to the UART. So if you have a laptop, you can do this on a laptop, otherwise you can write it on the board. But just mainly, I'd like to get, like, we keep going over this, but I'd like to keep going over all the steps needed to set up the UART. So if you remember the configuration steps that we need to do, and anything else that we would need to do to set up Hello World to a computer connected to the UART. Alright? And you can ignore peripheral pin select for now.
asterisks, or is that a?
It's an asterisk, it's a pointer. you have the example code from
Yeah.
the discussions? Okay. All right. I'll
Yeah, but that's not helping.
let's get this rolling. Okay, so
You got the example code. Should have an initialization function. Okay, so the first thing you do is you set up the tri-state registers, and then you set up the mode register and baud rate generator, and then you basically just set up the flow control, and then you enable UART and enable transmission. So you're setting up the input and output registers, the baud rate, and the flow control, and then you just enable the thing. And that's just all the little details that you got to do that. So we'll go over. Seriously, keep talking about it. I still don't get it.
No, no worries.
What's going on over here?
Yeah, it's not for this problem.
Okay, that big.
Yeah.
That explains something.
Any questions about the activities? Or? Okay, we'll keep going. How's it going?
Yeah.
Yeah, you can actually specify a string. So you wouldn't have
Yeah,
to
yeah.
have the right characters and a different string.
Yeah.
Set up for
Yeah. For 0 and 1. That makes sense.
So yeah, enable the UART, set the baud rate, and then set up things clear. Okay. Yep, you got it. This is not for the activity, but it's volatile unsigned char buffer. So I'm setting up a buffer and then putting a pointer to the top of the buffer. I think my syntax is correct. How's it going? Any thoughts or questions? Kind of got it figured out.
Copy and paste discussion.
Yeah, that's fine. If you had to change the baud rate, what would you do? And you might have to change the BRGH pin or the BRGH bit. Like if you need a faster baud rate.
Yeah, I think we put 25 in, right? For
Yeah.
38,000 Yeah.
Great. Cool. Okay, so the basic steps for doing this are you have to set up I/O pins, and then step 2 is you figure out your baud rate and configure the baud rate. But before you do that, you kind of just clear the U mode register. So clear U1 mode, and then set up baud rate. So that's the BRGH bit and the U1 BRG register. Alright, I'm gonna find a better black marker. So step 4 is what? Oh, question? Yeah, so
what's happening.
right off the bat, I think most of the example code would be clear U1 mode, just to make sure it's off, and then everything's starting from a blank state. Because when you clear U1 mode, you disable the UART, so it's kind of nice when you're configuring it to have it disabled. So that's why you do that first. So you set up the baud rate, this BRGH and U1 BRG registers, and then you set up or disable flow control. And we're never going to use it, so we're going to always write 0 to those 2 bits of the U1 mode. And then we're going to enable UART and enable transmission. And that's in U1 mode and U1 STA. And 6 is do the peripheral pin select, and I'll talk about that today. And that's the sequence of things that you have to do in the PIC to reprogram the peripherals with the specific I/O pins. And then 7 is enable any interrupts. Okay? So these are the steps you got to do to write hello world out. So once you write a UART initialization routine that works, you don't have to keep rewriting it. You can cut and paste it from your code, or maybe you want to write a library function or start building a header file that has all your initialization things in it. It's not a bad idea. For this class, sometimes it's nice to keep doing it over and over and over, though, just so you get it. So, all right, any questions about these steps? This is UART setup. You would probably want to interrupt for the receive. So when you receive a character, you probably want to save it right away. But you can also have an interrupt for transmitting. So when the transmission is ready, then you put a new character of the buffer out. So for writing out hello world, actually having a transmission interrupt might be nice, because that's the fastest possible way of sending out hello world. So you would just have hello world be loaded into like a global variable, and then each time the transmission was ready, you would send out 1 byte of your string, and it would automatically interrupt your code to do that. Does that make sense?
Could you repeat it again?
So you can enable interrupts for both receiving and sending characters, and depending on what your application is, you might want both.
Alright.
And if you have both, you might want to write a priority. So you might want to make sure, absolutely sure, that you receive everything, and then sending things might have a lower priority. Or you might have an application that's the opposite. You might have an application where sending things is the highest priority. And remember, this is like, it's like sort of the internet for the PIC. This is like how it communicates with the outside world. It's not like a clock pin or an I/O pin or anything like that. You can send stuff and receive stuff asynchronously. That's
That's why it's called universal asynchronous receive transmit.
So it's like a text message rather than a phone call. Okay. Are people waiting to, can I erase this? I took a picture. Yeah, that's fine. And then next in the class, we're going to go over a stack example with interrupts. And then we're going to talk about timers and stuff. So we're going to go over a stack example. Actually, we're going to talk about the peripheral pin select today. And then at the end of class, we're going to talk about timers. And then Friday, we might talk about timers, but it'll probably be mostly review. Okay, because there's a test on Monday. So you got a lab today and tomorrow. It's going to be a short lab, but it's also going to be a 2-week lab, so you don't have to stress about it during studying for the test. And then the test is on Monday, and I'm working on a study guide and another example exam, okay? Any other questions about the class? Okay. So, example, great. So this is the example code, and it basically just reads data into a buffer from the UART. So I've got some global variables up at the top. I think these might have to be extern. I'd have to check. So those might have to be external variables since they're outside of all the functions. But the idea is that you have a global variable that you can write to in the interrupt service routine, and then your main code can read it. So I have initialization, which will set up the UART. Then I just have a main while loop, and that just checks if there's a new value in the buffer. And if there's a new value in the buffer, I have an undefined function called push that puts the new character out on the UART. But I just want to focus on the interrupt right now. So the main code might look something like this. It's going to have like a main loop there, and it's going to say, oh geez, so if that is not equal to that, so it's going to be CP, let's say we're using W5, W6, and then branch branch if they are equal, branch if they're equal to loop back. And then if they are not equal, then we're going to do our call push one. We'll call this is our assembly language push function. And then we're going to move W6 to W5. And then we're going to branch loop back. Okay, so I just wrote this while loop here. So up there, we're going to have our call, init. I'm going to call them different names just to specify C versus assembly. And then for in assembly global variables, you can just have them be different working registers, or you can set up memory locations. But I really want to just kind of get to how interrupts work with the stack. Does this make sense so far? So basically W5 is PCH pointer, and W6 is the P old pointer. So if the address of the char character pointer changes, then it'll call Butch. Is this too complicated? Is this kind of making sense?
Sorry, just writing it down.
Oh, yeah, no worries. There's probably a million better ways to do this, but this is what I thought of off the top of my head. Okay. So the interrupt service routine is somewhere up here. It's probably going to be called something like U1 RX interrupt. And that's the label for the interrupt service routine. And what it does is it does bit clear I interrupt service flag 0, and I can't remember what number this is in the flag, but I'm going to do underscore U1 RX IF just to specify that that's the number. So literal is U1 RX IF bit. So it's the bit in this register. So we're clearing the flag. That's what we're doing, okay? So we're going to clear the flag, and then we're going to move, if our pointer is in W5, we're going to move U1 RX reg in W5. I think that's okay. And then at the end, anybody remember what the last instruction we do in an interrupt is? Yeah. Return from interrupt. Yeah.
On the right, the top right,
Okay.
the comment below it, yeah.
This thing? It just says that U1 RXIF is the interrupt bit. I'm not sure what bit it is, but it's just clearing the flag.
Oh, gotcha.
Okay. So now I want to show the stack, basically. I'm going to erase this. So how many bits wide is this? This is data memory. How many bits? It's data memory. It's 16. And, okay, yeah. All right, so we didn't show initializing the stack pointer, but let's say it's at 0x800. I think last time I did stack pointer over here. And anyone know what working register is? This stack pointer? W15, right? So this is 0x800. Okay. So we're in our loopback thing. Let's say there's no changes to W5 and W6. So we're just kind of going through here basically. And then when an interrupt happens, what happens? So say there's stuff we wanted to save. We can't do push and pop each. I mean, we could do push and pop each time through, but it might interrupt in the middle of a pop instruction, or it might interrupt in the middle of a push instruction. So it's not like calling a normal function, basically. It interrupts you. So you got to be, in assembly language, you got to be careful about what you're changing in the interrupt service routine. We have just something really simple going on. We have W5, which we kind of know throughout our entire program is a global variable. So none of our other routines will use it. W5 is like a global variable. That's the only thing that gets written in the interrupt service routine. So we're not touching other stuff, basically. So it's fine. We don't need to save stuff. It's not going to override anything when we call the interrupt. What we do need to do is we need to save the program counter because we need to get back. And we also need to save the status register. Well, actually, I don't think any of these instructions will affect the status register, but in general, the PIC does save the status register bits as well. And it also saves a global interrupt enable bit. So what it does is this. So it saves the program counter, save program counter, save status, and save I think it's intcon, some bit in intcon. So I'll call it global interrupt bit. It saves just the flags. Yeah, it doesn't save the whole thing. So how many bits are in the program counter? That's right. 24. So we need at least 2 memory locations to save. So I believe what it does is it saves the low bit of the program counter first, the low word of the program counter. So this is where we got interrupted. So we save the low byte of the program counter first, and then we save the low word. Then we save the high byte to PCH, and then we save this global interrupt bit, and then we save status flags. And then the stack pointer is here. Okay. So this is after the interrupt happens. I can't really write it out in the code because I don't know when it'll happen. It's controlled externally by the hardware. So this is our stack. And then when we return from the interrupt, then we load the things in reverse order. So we load the high byte, I guess, and then the global interrupt status, and then the status flags, and then the low part of the program counter to go back to whatever part of code we were in. I don't know. What happens if we want to save anything else? We could push it on this. Oh, go ahead.
I have a question.
Yeah.
So with the interrupt, you within that same interrupt, correct?
That's right.
So, to answer your question, then can we just push everything at the top and then pop it in reverse order at the bottom of the unit?
Yeah, you could. Yeah, but in general, you don't usually push and pop from within an instruction, and or from within a subroutine. But you could do that. Another thing is that doesn't work then if you do have multiple interrupts with different priority levels. But like in our class, we're not really too worried about that. In our class, we're not really worried about this in general because we have so many working registers that we can just specify certain working registers as being global, and then the rest won't get touched by the interrupt, and therefore it won't be a problem. Another thing you can do is you can have one working register be destroyed in an interrupt service routine, and then just specify a memory location that's your global variable, and then that will be safe for all instructions. But there's a third option that the PIC24F provides. So you can specify working registers as being global. You can specify a memory location in your code that's global. And there's also something called shadow registers. And so the way the PIC implements those is that there's an instruction called push.s, and that saves working registers 0 through 3 in shadow registers. And then at the end of before you call retfee, at the end of your interrupt service routine, you can do pop.s and restore those. So if your interrupt service routine messes up working registers 0 through 3, you can save them and pop them. Yep.
Push.s and pop.s to all 4 registers at the same time, correct?
Yeah, in one instruction cycle. Yeah. They also save every bit of the status register additionally, except for the don't care bit, or the DC bit. I forget. I think that's the half carry or something like that. But it's one that doesn't get used as much. So it's what we could do is in our code we could do push.s and pop.s and then ret. But our interrupt service routine doesn't mess with 0 through 4 anyway, so it's not super important for us. But those seem like they would be stack instructions, but they're not. So we've got our data memory here, right? And then we also have our array of working registers. These two things are 16 bits wide, but they don't look like it. So this is W0, W1, W2, W3, dot, 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 W14, W15. And what the push.s does is it saves these into a little background register. They get saved into each one of these gets saved into a background register with push.s. And then when you do pop.s, these background registers get restored. And so it's kind of a handy one instruction way of saving these 4 working registers. So W0 and 1 are divide registers. So if you have a divide instruction executing, it's kind of important to save those because the divide instruction, you execute it multiple times and it accumulates in W0 and W1. So it's important to save those. For multiply, it could be important as well if you're in the middle of a multiply instruction and you get interrupted. And just in general, W0 through 3 get used a lot in as just generic working registers. Okay, it's just so more complexity to the mix, but it's a handy thing to be able to So you do pop.s and then you do return from instruction and everything gets loaded back and hopefully unchanged. Except for W5 because we do want to know when we have something in on the UART. So it's just a little bit of finesse involved with interrupts. Just got to be careful that it's not. You got to be aware of what you're changing in your code. And when you're writing in C, if you use global variables, then it's a lot easier to take care of everything. In assembly, you have to be very careful. So it's another reason why writing in C kind of starts to make a lot more sense, because you let the compiler take care of all this stuff. All right, I think I have some slides from the manual. Okay. Okay, so this shows shadow register usage. The pop.s and push.s save the status register and W0 through W3. In the DS-PIC30, there's there's something called do registers that get saved with push.s and pop.s. That's peripheral pin select. Okay. So in the programmer's manual, there's descriptions of the push.s and pop.s, but they basically just save the working registers. That's what they do. Okay, so now I wanted to talk really briefly about the frame pointer. My example last time, I kind of said, okay, the frame pointer W14 is at some memory location way down here. That's actually not true. The frame pointer is part of the stack. Okay. So this kind of series of slides just shows kind of how the frame pointer works. So here's some example assembly language where we got a subroutine that we're going to call. We got a link instruction there, and we're going to see how the frame pointer works. So first, before we do the first push instruction, we've got the frame of task A, okay? So W14 is somewhere up there. And then we've got the stack pointer, top of stack, that's in that new memory location. So task A got called from the main function somehow, and we're sitting in task A. We've got a frame pointer for task A, but we don't really know what else is going on, okay? So this is after we've done all the pushes and the calls. So we've pushed W0, W1, and W2, and they're listed on here as parameter 1, 2, and 3. And then when we do a call, we save the program counter, and then we're at the top of the stack. The frame pointer hasn't changed yet. After we do the link instruction, then what that does is it sets up it saves the frame pointer on the stack right after the program counter, and then it moves the frame pointer to the top of the stack right after the old frame pointer. And then it moves the stack pointer however many words the frame pointer is. So the frame is on the stack. That's the point I wanted to make. And so link number 4 will allocate 4 bytes or 2 words. And so that moves the stack pointer up 2 words. Saves the old frame pointer, moves the new frame pointer to the new frame, and then it moves the stack pointer up too. And so it makes it easy to check if your frame is greater than the stack pointer, then that means you've exceeded your frame. So everything's kind of bounded and on the stack. The frame pointer isn't off somewhere else in data memory space. It's right on the stack. Makes sense? Clear as mud? Should I do a quick example?
Yes, please.
Okay. So I got an R call push right here. So we came back from our interrupt, and we got something new on the buffer. So our stack pointer is back to 0, and then we're going to do rcall push, and push is just down here, and push has link, say link 4. Dot dot dot, and then ULNK, and then return. So for right here, we don't save, we don't have any push or pop. I could add them if you want, but for now we don't have anything. So when we do the R call, we save program counter high, program counter low, and then our stack pointer is here. Our frame pointer, where is that? I don't know. We haven't set it up yet. So our main function doesn't have a frame. Yeah.
What would that be for? Is it just creating space on the stack? Is that the whole purpose?
Yeah, it's if you have a local variable in a C function, that's basically just a frame on the stack. Because after that function returns or executes, you don't need that space allocated in memory anymore.
Oh,
Yeah.
oh, in a function. Okay.
Yep. Yep.
What if we declare a variable in a local function that is static? Would that be something completely different away from the frame?
So static would mean that when you call the function again, it should still be there. That should do something different away from the stack. Yeah, that should maybe make some local space. It depends on the compiler, though. In general, that's usually not a good idea, because if you have something that's static, you can only access it in that function, but it takes up space for every other function. So I think for embedded system programming, that might be a bad idea in general, but there may be some applications for it. That being said, I don't know what that would look like. I'm guessing it wouldn't be on the stack because the stack, the frame pointer gets deallocated once you're finished, okay? So we've got we called the thing, we called the push, and then we've got a link coming up. So what that does is it puts the frame pointer right here. It saves where it was before first, which we don't have it, but say we did. So save, let's call this W14 old, and then it puts W14 here. And then we got link 4, which is 1, 2, 3, 4 locations, and then it moves the stack pointer up that far. And now we're all set. And then when we do unlink, that means the stack pointer can go back however many we linked. So the stack pointer can go back here. The frame pointer gets loaded with its old value, wherever that was. So the stack pointer is back over here. And then we're ready to do a return, or reload the program counter back. And these values in memory might still be there, but we don't need to clear them or anything, but they'll get overwritten next time we do let's take a break. How about 9:10? Come back. Yeah. Yeah, but it's on the main stack. It's like a local stack, but it's on the main stack. Yeah, but so the stack has like a program counter, might have status registers, and it contains the old frame pointer. The frame pointer is like a stack within a stack, but the frame pointer is not going to automatically store program counters or status registers. So it's more just like a local bit of space. There's no push for the frame. You just do W14. But if you do the link and unlink and you do W14, you don't have to exactly know where W14 is. Yeah, right, exactly. And when you write your code with the frame in mind, you'll know how many bytes you need to allocate. Yeah, when you it's up to you. You can push stuff and then use. So if you wanted to pass a parameter in W0, you could push it before you call the function. But remember, the stack is mainly just for saving things. So if you wanted to pass a parameter in W0, you would just have it in W0, and then the subroutine would just use W0. You would have to know that. Okay. Or you could have a memory location that you use to pass variables. But your frame, as far as I know, your frame is really kind of like a local variable space. I really don't have to pass things on it necessarily. If you pass something on the stack, then you have to, then the stack will automatically get incremented for the program counter and maybe the frame pointer. So you have to know how much to decrement the stack to find the passed value on the stack. So I don't think it's designed to work that way. Okay. Thanks. Yeah, thank you. Yep.
It's gonna take 4 weeks. It's gonna take twice that amount. So.
I'm gonna post it as soon as the class is done.
Yeah.
Alright, let's get started again. I got a quiz for today. Alright, so this is a baud rate thing. So if you want 9600 baud, the instruction frequency is 16 megahertz and BRGH equals 0. What would you want to write to the U1 BRG register? Yeah, sorry, this one's kind of hard. You can share answers among tables if you just want to have one person calculate it.
No.
Yeah, so that calculation thing is kind of nice because
I squared C for yeah, that's the right one. So the second frequency is 16 megahertz, and you just put 1 million on top, and then you divide it by the baud rate.
Couple more people. Okay, is that everybody? 2, 3, 4, 6. Okay. So most people got it. It's 103. 25 is confusing because that's what we used for 38,400 baud. But it's 103 for 9,600 baud. All right. Yep.
If it were ERGH equal 1, now that's 4, right?
Yeah.
How is that
So
changing the formula?
in the formula for, so we're using the formula for calculating what goes into U1 BRG. You divide by 4 instead of dividing by 16.
Like 16 times the baud rate?
Yeah, 16 times the baud rate.
So it'd be 4 times the baud rate?
4 times the baud rate divided by 1600. So it would be a bigger number, right? It would be 412. No, it would be 415, I think. So it would be 104 times 4 minus 1. I don't know. Next question.
The formula here shows root x BRG, so that x changes.
Yeah, the x is either 1 or 2. We have 2 UARTs. So if you wanted to connect to 2 computers at once doing completely different things, you could.
So in that case, the formula would be
It would it be different? I think it would be the same. Yeah. Okay, next question. This is something a little different. This is you write in an answer. It's just your thoughts, your personal thoughts that you can put up here. And think on the test, I'm going to have at least one question that's just going to be a writing. Just write, explain what something does. Is everybody typing or? Okay. That's okay. read them unless people want me. Is everybody okay with me reading answers? Okay. I won't call people out. It's not nice. Couple more people maybe. Is everybody finished that wants to submit something? Oh, okay. Alright, well, I'm just gonna see what this does. Okay. What purpose do... This is cool. Okay. To trigger code when an event happens in the physical world. Yeah, that's great. I think that's a great description. To interact with its environment. It's good. Stop the current program, puts the attention of the hardware to the current interrupt. That's exactly what it does. They allow for something comparable to multitasking. Yep, that's right. That's good. Oh, this is great. Interrupts give us the opportunity to save our location in terms of the program counter and do an alternative task. Alternate task. Will elite speak? That's good. Okay, interrupts the main process to conduct a priority process. Yep, that's good. To allow a higher priority task to complete immediately before completing the program. That's a good description because interrupts don't necessarily have to be from peripherals. You could have an interrupt from a timer that basically is just doing something internal to your program. We haven't really covered that yet, but it's good to identify that. They allow a program to break out of a power save mode and perform a function when information is given. That's good too. It's not just for power saving modes, but you definitely would want an interrupt type thing if you're going to be in power save. Stops program and figures out what to do. It's not super descriptive, but that is what happens. What interrupt do is the interrupt execution and follow precedence to perform another high priority operation execution. Yep, great. Allow for priority execution of tasks, serve as means of error handling, good. Yep, looks great. I'm gonna keep moving here. Next question. Anybody still typing? All right. All right, everybody ready? Show results. All right. Way to store and save information while being easily accessible. That's a pretty good description. Allows us to store useful information, i.e. our PC. We decide to break chronological run through. Organized way of addressing memory allows the user to control memory size. This is to prevent working regs getting destroyed. SOR, save our working registers. Okay. Yeah. Not to be confused with fat stacks. So. Okay, I like this one. This is good. It is means to save valuable info such as the PC or regs before a function is called and restore that info after the function returns. It always stores the program counter. Okay, the rest is optional, but it does provide basically a software interface for storing variables. But it always stores the program counter when you call and return from functions. It's the main use is calling functions. That's what the stack is useful for, saving stuff when you call functions. But it looks like everybody got the idea. All right. So that took a bit longer than I wanted, but I wanted to get kind of in the tests. There's going to be a question or two that's going to be a writing question. So I wanted to get a feel for how that was going to work. And it worked great. Okay, so for the rest of the class, I want to talk about peripheral pin select and the timers. All right, so peripheral pin select is this thing that I kept putting off, and it's the thing that gets used when you want to hook up the UART. It's one of the steps that you have to do. So in the data sheet, it says you got to follow a certain routine to enable peripheral pin select. So you have to write a command sequence, then you have to unlock IO lock then you have to figure out what to write to these two registers. Actually, there's a bunch of registers. There's one that is you figure out which input pin number to write, and then the other one you write to a port and you figure out which function number. It's really confusing. So for the UART, say you want to output it on pin 8. So what you do is you find the R pin register that's associated with UART. This is for input, so this would be UART RX. So to do PPS, step 1 would be figure out RX. That's receive, that's input. So you have to figure out which RP INR corresponds to the UART RX. Okay, so we're going to look in the data sheet. Gotta load it up. I'm going to look in the data sheet under I/O ports. Okay. And we got all the port A, port B stuff, and then we got controlling peripheral input select, input mapping. So we look at this table 10.2. It says selectable input sources maps input to function. So we look at UART1 receive. That's RP INR 18. So we need to write to RP INR 18. So RP INR 18 is a 16-bit thing. So I'm going to draw it as two 8-bit things. And it says that part of RPINR 18 devoted to UART receive is bit 0 through 4. So if this is bit 15, this is bit 7, this is 0, 3, and 4. So change the, oh, yeah, sure. Is this better? Okay. Can you read this stuff up here? Okay. RPINR 18 is for UART RX. Does that just look like garbage now? Okay. Probably should erase that first. Okay, so it says that these bottom 4 bits we're going to use for UART RX. And what goes in here is the pin number. So it says it somewhere. Input mapping. Okay. The RP are used to configure. Each register contains 2 sets of 5-bit fields, each associated with one of the pin selectable peripherals. Programming a given peripheral's bit field with the appropriate 5-bit value maps the RPN pin with that value to the peripheral. For any given device, the valid range of values for any of the bit fields corresponds to the maximum number of peripheral pin selections supported by the device. Okay, so we've got 5 bits. How many pins can we select with 5 bits? 4 bits, how many? 16, right? So we can do 32. So how many RP pins are there on our device? There's up to RP 15. So we don't actually need 5 bits. So this is the RP and goes in here. So whichever RP you want. So you got to look at the pin diagram. If we wanted to go on pin 8, we can't. We could go on pin 15 though, which is RP6. Okay, so pin 15 is RP6. So we would put the number 6 in here. Okay, we put the number 6 in RPINR18 bits 4 through 0. That configures RX as an input. These bits are associated with the UART RX, and the number 6 is associated with pin RP6. So that's the input. Now for outputs, again, this is, so figure out TX, that's output. It would be nice if there was like an RP O and R, like output, that's associated with the UART TX, right? And we could just program whatever pin in there we would want. It's associated with the output. That's not how it works. So instead, there's a register associated with each output pin, and then you program in the function into that register. And okay, so there's now we got to figure out, the way it works is you figure out what output pin you want. So let's use pin 16 RP7. So pin 16, that's RP7. We want to use as our output. And so we find which there's a register associated with that pin. So output mapping. In contrast to inputs, the outputs of the peripheral pin select options are mapped on the basis of the pin. That's really annoying. In this case, a control register associated with a particular pin dictates the peripheral output to be mapped. The RPOR X registers are used to control output mapping. Like the RP INR registers, each register contains 2 5-bit fields, each field being associated with one RPN pin. Okay? And it has this table that shows function, output function number. Not sure what that means yet. So we figured out what pin we want. And now we have to find where the pins are. So it says see register 1015 through register 1027. So let's go to register 1015. That's RPOR 0. Is that going to be RP 0? Okay, yeah, it's RP 0 and RP 1. Okay, so we want RP 7. So let's go down to RP. Okay, so we want pin RP 7 that's in R4 3 bits 8 through 12. Okay, so this is tells you what goes into RP7. So what RP7 is mapped to. So R4 3 is this 2-byte register, and it's got 0 through 4. And it's also got it's also got 8, 9, 10, 11, 12, 8 through 12. And these are associated with RP7. So it's R43, RP7, pin 16. It's a lot of numbers, and it's really complicated the way they've done this. And it's completely different than mapping the peripheral pin select for inputs. So what we put in here is the function, the functionality that we want. So this tells you what pin it is, and we got to put the function number in here. The function number for UART transmission is in table 10.3, and its U1TX is output function number 3. So we put in R, we put function, which is just the number 3, into R for 3 bits 12 through 8. So we just put the number 3 in here. The number 3 corresponds to UARTX. So that's UARTX. UARTX in table 10.3 is function 3. Table function number 3 goes into R43. They're not related to each other. It's 12 through 8, which is R7. Confused yet? Yeah, it took me like an hour to figure all this out. Okay, so we got our UART, right? We need an input and output pin. So we pick our input and output pins, and we make sure that they're RP pins. That means that we can write to them with the PPS. And we make sure that we don't need to use those pins for anything else. So we know that one of them is an input, one of them is an output. So we write the correct tri-state buffers to configure the TX as an output and the RX as an input. Then we need to do the peripheral pin select to connect that pin to the UART. And for figuring out the input, there's an input register associated with the UART receiver. And we program the pin number into the UART receiver register. That's the input. For the output, we're connecting the UART transmitter to the output port. And so we program the output port register with the UART transmitter function number. Yep.
Say hypothetically, that's crazy. I just put like the UARTX function on every single output register. We're just firing out transmit from the same thing.
Ooh, that's a great question. I don't think, not sure if you can connect it to more than one, but you might be able to. I will get back to you on that. How about? Not sure. Let's see. Oh, many outputs. Okay. So the way I kind of think about this is, so we've got our UART. It has an RX and it has a TX. Got our little UART block. And then we've got all the pins over here, and they can connect to anything. So this is like, they call it, we'll call this RP. We've got this RP block. So the UART, let's say for receiving, the UART kind of has its own receive thing. So for the receiver, it kind of has its own thing here, and that tells you which pin it's going to connect to, and the RP here. So this is RP, I, and R18. And for the transmit, for the output here, each pin kind of has its own port. So this is way too small, sorry. So, I don't know. I'm just going to draw a little box here. R4. So the receiver the receiver has its own register associated with it, and the transmit has to be connected. Each output has its own associated. So what I want to make the distinction of is the outputs are controlled by the RP thing, and the inputs are controlled by each module. So the outputs are defined by the pin for the PPS. Outputs are defined by pin, and inputs are defined by the functionality, the UART or the ADC or anything else. That's the way they've done this. To me, it's very, very confusing. But hopefully it makes a little bit more sense. And again, this stuff is not, this is detail. It's not going to be like on tests and stuff. But if you're wondering, if you want to change the code and to figure out how everything works together, it's helpful to know this. Questions? Okay, I recommend the only way to really get through this is to read through the data sheet like 10 times, basically. And to maybe I'll post some example code that just Charles Renoulet, I believe, used to teach the class, and he had a header file that he would just call, and he wouldn't make his students look at this at all. He would just say, pass the parameters to the header file, because it's complicated and it doesn't need to be. It doesn't need to be this complicated. Okay, so if that's not complicated enough, you have to do this write sequence in order to configure these registers. You have to write 46 hex to OSCON, and then you have to write 57 hex to OSCON, and then you have to clear the IO lock bit, and then you do all this configuration, and then you do that again. You write 46, write 57, and then you would set the bit to lock it back up. So you unlock it, you configure everything, then you lock it back up. Okay? So this type of thing is just screaming to be in its own header file so that you don't have to look at it each time. So maybe I'll see if I can write something up. Otherwise, for the labs and everything, this will be provided. Okay. All right, so I think that's all we got for today. I got some surveys if you wouldn't